So we've looked at the basic counting idea, then permutations in general, then combinations. So when we're doing an exercise on one of those things, life's a little bit easier because we know which one it is. The reality is when we see a question, we have to make a decision. What technique am I going to use? Will I use the basic counting principle? Will I use the idea of permutations? Will I use the idea of combinations? So let's look at a few here where we're not told what type it is. We have to make that decision for ourselves. So going back to 2007, boy, Mr. and Mrs. Roberts and their 4 children are going to the theatre. They're randomly allocated 6 adjacent seats in a single row. What's the probability that the 4 children are allocated seats next to each other? All right. Order, important or not important? So we're going for permutation? Let's see. Well, it's a probability question, so the first thing I want to work out is total number of arrangements, no restrictions. And so, sure enough, that's a permutation, isn't it? Because the bottom of the fraction is how many ways can we arrange the 6 people? 6 factorial. So on the top, how many ways can we arrange the 4 children and Mr. and Mrs. Roberts? Well, gosh, let's explain all this. The children have to go in a group because they want to be next to each other. So therefore, within their group, they can be arranged 4 factorial ways. But now we treat them as if we've got 3 objects, the 2 adults and the group. And so there's the 3 factorial. So 3 factorial, 4 factorial, on 6 factorial, a 1 in 5 chance. Okay, also 2007, this one came from an extension 2 paper, so a little bit more involved. A bag contains 12 red marbles, 12 yellow marbles. 6 marbles are going to be selected without replacements. Calculate the probability that exactly 3 of those marbles are red. 3 marbles are red. Okay. Probability 3 are red. This time it's a combination. Because the actual order we pull them out, we don't care. We're just looking at what are the marbles when we pull them out. So the bottom of the fraction, 24C6, I'm just choosing 6 from the 24. The top of the fraction, 12C3 by 12C3, because of the 12 red marbles, I want to get 3. And of the 12 yellow marbles, I want to get 3. So 12C3 times 12C3, it turns out to 2 decimal places, 0.36. Hence or otherwise, calculate the probability that more than 3 of the selected marbles are red, giving our answer correct to 2 decimal places. Well, more than 3, so it'd be 4 red, 5 red, or 6 red. So 4 red, 12C4, which means 2 yellow, 12C2, plus 5 red, 12C5, 1 yellow, 12C1, 6 red, 12C6, and none yellow, 12C0, over 24C6. And there's our answer, 0.32. But the interesting thing about this, it says hence. Now, hence means using what you've already worked out. I haven't really used what I've already worked out here. I went or otherwise, and that's fine, you can go or otherwise. But it does bring up the interesting question of how do you use part I to get an answer? So have a look at this one. Probability of greater than 3 red will equal 1 minus the probability of 3 red minus a probability of less than 3 red. So now I am using the complementary idea. Well, the probability of less than 3 red would be the same as greater than 3 yellow. But the probability of greater than 3 yellow is the same as the probability of greater than 3 red. So I can treat this like an equation now and move the probability of greater than 3 red to the left-hand side. So I have 2 lots of the probability of greater than 3 red is 1 minus the probability of 3 red, and that's what we worked out in part A. So it'll be half, because I don't want 2 lots of the probability, I only want 1 lot, but 1 minus the answer we got before, and we end up with 0.32, the same answer. So that's how I could have used part I. Another extension 2 question. This one was a beauty. Follow this one carefully. In a chess match between the home team and the away team, a game's played and there's 4 different boards. On each board, the probability that the home team wins is 0.2, the draw is 0.6, and the home team loses, in other words, the away team wins, is 0.2. Now they record their results down. And the way they record it down is simply writing a WD or an L, win, draw or a loss. So, and they've given us an example here. If the home team wins on board, that should be board 1. Can't be on 2 boards, of course. Home team wins on board 1, draws on board 2, loses on board 3, draws on board 4. That would be WDLD. How many different recordings are possible? Well, on the first board, you could either get a win, a draw or a loss. On the second board, you could either get a win, a draw or a loss. On the third board, you could either get a win, a draw or a loss. On the fourth board, you could either get a win or a draw or a loss. So 3 times 3 times 3 times 3. There are 81 different ways the game could end up. We'll calculate the probability of that win, draw, loss, draw. Well, probability of a win was 0.2, so 0.2 for the first board. Probability of a draw was 0.6. Probability of a loss was 0.2. Probability of draw 0.6. So the probability of win, draw, loss, draw is 0.144. Teams score 1 point for a game won, half a point for a game drawn, and no points for a loss. What's the probability that the home team scores more points than the away team? First thing I'm going to do is work out what's the probability they get the same number of points. So how many ways? There's lots of different ways they could get the same number of points. You could end up with 4 draws. If they draw on all the boards, they'd get the same number of points. So 0.6 to the power of 4, 0.1296. That's one possibility. We could have 2 wins and 2 losses. Both teams would end up with the same number of points then. So 2 wins and 2 losses. Well, a win was 0.2, and there's 2 of those, so we'll get 0.2 squared. Losses was 0.2, so that's also 0.2 squared. But then I multiply it by 4 factorial and 2 factorial, 2 factorial. Why? Why am I doing that? Well, that probability that I worked out was win-win, loss-loss. But it might not have been win-win, loss-loss. It might have been win-loss, win-loss. Or it might have been loss-loss, win-win. Or it might have been loss, win-win, loss. Or it might have, you get what I mean? There's lots of different ways. It's now like saying, how many ways can we arrange the letters W, W, L and L? And we've seen those questions. So that would be 4 factorial divided by the repetitions, 2 factorial, 2 factorial. So we get 0.0096. What else could happen? Oh, a win, a loss and 2 draws, couldn't it? That would come up with it. So here we go, win, a loss and 2 draws. So it'd be a 0.2, 0.2, 0.6 squared, but multiplied by, how many ways could we arrange W, L and 2 Ds? Well, that'll be 4 factorial and 2 factorial, 0.1728. I think that's it. There's no other way we could get equal points, is there? Okay, so equal points ends up being, adding those 3 things together, 0.312. Now, why did I do that? Because now I'm going to use the complementary idea. That was the probability of equal points. Therefore, the probability of unequal points is 1 minus that. Now, if it's unequal points, that means one of the teams has won. One team's got a different number of points than the other. Someone must have more points than the other. But everything was equally likely. So therefore, the probability that the home team wins must be half of that probability. Because half of it would be home team winning, half of it would be home team losing. So we end up with 0.344. 2002. Pack of 9 cards numbered 1, 2, 3 up to 9. 3 cards are drawn at random and put down on a table from left to right. It forms a 3-digit number. So you just read it from left to right. What's the probability that the number exceeds 400? Is bigger than 400? Okay, well, what makes a number bigger than 400? Well, the second 2 numbers are irrelevant, aren't they? It's the first number. So greater than 400 would be 6 on 9. Remember, there's no zeros in this pack. So the numbers that come after the 4 must make it bigger than 400 if that first digit is bigger than 4. So, or 4 or bigger, sorry, not bigger than 4. 4, 5, 6, 7, 8, 9, 6. 6 ways we could do it. So 2 in 3 chance. What's the probability that the digits are drawn in descending order? Now, it doesn't necessarily mean they're consecutive, as long as the numbers go down in size. Well, we know just arranging the 3 digits is going to be 3 factorial ways we could do it. Of those 3 factorial ways that we could arrange it, so we get 3 digits. There's 3 factorial ways we could get those 3 digits. I'm now going to put those 3 digits on the table. How many ways could I arrange them such that they're in descending order? Let me put some numbers behind it. Just say you drew the numbers, I don't know, 3, 4, 5. Can someone please arrange those digits in descending order for me? So 3, 4, 5. Anyone want to put it in descending order? 5, 4, 3. Okay, there's one way of doing it. Can anyone tell me another way of doing it? No, there's only one. Therefore, the probability of them being in descending order is 1 in 6. Now, there's 6 ways I can get 3 digits, and only one of those ways they'll be in descending order. So probability of 1 in 6. All right, 14F. We're going to do all the strange questions.